building rockets in the 13th century to repel the Mongol hordes coming from the west to the east into China. Whether you were doing work with Archimedes and his steam engine that whizzed around back in the ancient days of the Greeks, the same principles work for the space shuttle or newer model rockets here, and they were defined a long time ago by Sir Isaac Newton in, I think, about 1657. And as I recall reading this, and it's a fascinating biography, they called his school off. He was in Cambridge, and there was a case of plague going through the area. And so they said, well, let's hold school off until this thing passes. So he kind of got a 2-year sabbatical. He went to a relative's farm, and the legend is, you know, that he was sitting underneath a tree and an apple bonked him on his head, and he said, what happened, why is that? I don't know if that's just hearsay, but he did take the time to write his treatise in Latin, which was natural mathematical principles. You know, that was what he called it. And in there he described the 3 laws of motion. And they are the ones that make your rockets work, so I'm going to inflict on you now those 3 laws of motion, okay? And the first one was called the law of inertia. The law of inertia, he said, was that if you had something at rest, like this rocket, it would stay at rest continuously, unabated, for all time, until something made it move. Earthquake, janitor comes in, rocket takes off, something like that. Now, when it does go, a body in motion, a rocket moving, it will go in a straight line, and it will go continuously forever. Likewise, until it's acted upon by some force, such as hitting the ceiling, or can't quite get to the sun because gravity brings it down, or wind blows it. But that is a concept that, even though I'm an old man, for me it was a difficult one to wrestle with, because the principle is that it just keeps on going. And I just could never visualize that, because my experience in life has been things stop it. But the theory is that that's the way it worked. The first person to launch a liquid-fueled rocket, which brought us into this era, was a fellow by the name of, do you know his name?
Nope.
That wasn't his name. His name was Robert Hutchins Goddard. He launched the first liquid-fueled rocket on March the 16th, 1926. And, okay, so that's less than 100 years ago. It's about 85 years ago, so 86 maybe now. And he said, okay, using that principle, I should be able to launch my rocket, and it should be able to go to the moon by the second principle, or the first principle of inertia and such. And people said, you've got to be kidding. Even physicists said it. Said once it gets out of the atmosphere, there's no air to push against. So therefore, the rocket couldn't possibly go to the moon. So within the last century even, this idea of inertia was not really understood, even by, it was not really accepted by some people. But that was the first law of motion, which is inertia. A body at motion will stay in motion in a straight line and continuously. All right? No problem with that. You got that one. The second one was changes in the body of motion, which he called the law of acceleration. And he said that the change in a body's motion is going to be directly proportional. Anytime you hear that word directly proportional, you know there's a mathematical function that's associated with it. But anyway, that was your key word. It's directly proportional to the force that's acting on it, the direction of the force, and the amount of force that's acting on it. So if this is going on a straight line, and gravity takes it and makes it come down, then it's going to be because of the amount of gravity and the direction that gravity is coming from. Another thing, they call space, when they go on the International Space Station, they don't normally call it a weightless environment. The true scientists and mission people aboard, they call it a microgravity environment. There's still a little bit of gravity. In fact, everything out in space has a gravitational field. It's hard to believe, but even a pencil would have a gravitational field. So if you've got a lot of little BBs or rocks or iron chondrites out in space and they're in proximity, eventually they will kind of accrete together, and we call those accretions the planet Earth, okay, or the moon. So we've got a lot of asteroids out there and such. They eventually, they generate a gravitational field too. So that was the second law of motion. The way they worked it out mathematically is they came out with a function which said that the force that's generated on something is equal to how big it is, its mass, times how fast it's traveling or its acceleration. So force equals mass times acceleration. So if you have a big, big object, but it's traveling very, very slow, it can have the same amount of force as a little teeny object traveling very, very fast. In some of my other classes, I talked about my friend's speed bump. I was going to tell you his name, but I suspect that Raza is recording this, so we'll just call him Speed Bump. But he was working on his Volkswagen minibus, and he was working underneath it. He attached 2 wires, and Joe had started up, and the minibus proceeded to, it was in gear, to roll over him, much to his chagrin, and then down the driveway. And it must have been excruciating because it was going like a half a mile an hour. You imagine being underneath this thing and seeing what's going on. And then you know it's going to crash into the neighbor's house. So he got up, not worrying about fear or what would happen to him, ran down the driveway and jumped in there and stopped it. And then at that point he decided to check, ribs and everything. It had a lot of mass, but it was traveling so slow that it had very little force on him. Okay, but if you could take a little piece of metal, just say half an inch, maybe an inch long, and make it travel several hundred feet a second, they have a name for it. They call it a bullet. And those things go. And you have to worry about bullets out in space. We have 5 spaceships that are traveling around the Earth now called in the A train. It has nothing to do with Duke Ellington. But they all follow the same orbit. And one looks at ice, and one looks at land mass, and one looks at sea, and they all have different purposes, and they have different spectra that they look at. But since they're in the same orbit, they pass over the same area at the approximate same time. And so they call this a train, in the A train. And every now and then we track pieces of space debris, and the space debris, it comes in there. We have to elevate that entire train of spacecraft so it doesn't hit one of these little things like a fleck of paint, Jenkins, can put a hole through the space shuttle window. So that you really have to watch it. Small objects traveling very fast exert a lot of force. And those are a couple of examples. Let me pause. You guys probably know this. How fast does an object have to travel in order to stay above the Earth in orbit?
So we all.
Well, the answer is 18,000 miles an hour. You work it out, that comes out to 5 miles a second. You could be back at home in 3 seconds or less. Except for Diana and I, we have to travel how long? 7 seconds, huh? 8 seconds?
Ooh, an extra 4 seconds.
Yeah, something like that. So anyway, so enough of that. That's the second law of motion. And there will be a quiz, by the way. And the third law of motion is, for every force there's an opposite and equal opposing force, or for every action there's an opposite and equal reaction. So I guess if you had to put it all together, this will stay on the launch pad until it's acted upon by some force, and that's in case that what happens here is the rocket ignites. When the rocket ignites, gas is expelled out of the back end of the paper here. The back end of the paper is bell-shaped, has a nice little nozzle. It expands the speed of the gas, making it travel faster, and that exerts the change of direction and the force to make the rocket go up. And as it goes up, you have an action here, that's the reaction. All right, that's putting all 3 of them together.